Hi everyone. Looks like I've got a lot of presents here. Any more homework assignments? There's a stapler, by the way, in the technician's room right around the corner, so you can staple your work before you submit it. It's just in Patrick's area there, and he's happy to have you use it. Here are the class notes for tonight. We've got kind of a beast of an in-class exercise that we're going to be working on, so I want to leave plenty of time for that. We traditionally have a hard time getting through all of those in-class exercises, but this one's actually quite long, so we'll try and fit it all in tonight. I'll give you homework number 3 in class next week, and then it will be due 2 weeks from tonight. So you'll have a week to finish that. And it covers some of the things that we're going to be covering in class tonight, mostly, and then a little bit from the lecture next week. Just as a reminder, many of you are still thinking about what topic to use for your research paper. So please let me know when you've selected that, and I'll mark it down on the paper. Most of the topics are still available. All right, so let's get into it. We're going to be talking about modeling suspended growth tonight. And we begin with the important idea of mass balance. And we've talked about mass balance before, and I'm sure that even before this class you had mass balance as something you had to think about. But the idea here is that if you have a control volume, and we can just represent that control volume as a box. It's an imaginary space, and if you keep track of what goes in to the control volume and what goes out of the control volume, let's say that there's some mass in that control volume, and if it's a tank of water, for example, what we know is that the difference between in and out results in accumulation. So think about, if you have a big flow rate in, much larger than the flow rate out, then the water level in the tank would begin to rise. And so that's accumulation. And it works whether it's a liquid, whether it's a solid, or whether it's some substance dissolved in a liquid. So it could be the accumulation of material like BOD, just as an example. So sometimes when I'm writing on the board, I'll just abbreviate that ACC, meaning accumulation, is the difference between in minus out. Now, that assumes that there's no reaction happening inside of the mass, inside of the control volume. But we do have reactions. Here you can see in the picture a big surface aeration device, and I'm a little uncomfortable with how close that guy is standing to the splash zone. I'd take a few steps back, but he's talking into a walkie-talkie, so he's pretty official. Yeah, it's going to be splashing his face, right? All right, so inside the aeration basin, there's a reaction happening. And that's the whole reason that we'll have jobs as environmental designers, is because those bugs in there are doing a reaction, and we need to design the reaction. So this is an oversimplification, just the idea of mass is in minus accumulation is in minus out, because we have to keep track of what's happening inside the reactor. And so we can do that. It's no big deal. So we have to get away from the assumption that conditions are always going to be in steady state. And steady state means that flow is fixed over time. And of course, when we sized our flow equalization basin, we got a brief exposure to the fact that wastewater flow rates are not constant over time. And what we're going to take a look at really addresses is the fact that there is a reaction happening inside of the control volume. So these two assumptions aren't always true. In fact, they're very rarely true in wastewater treatment because the flow rates are variable, but more importantly for tonight, the bacteria grow inside of the aeration basin, and they reproduce. And that process is turning substrate into new cells. Who can remind me what the word substrate means? Food, right, right. And so what do the bacteria use as their food? What are they eating? They're using the oxygen demand, whatever it is. That oxygen demand might be the food scraps that you flushed down the toilet, you know, or it might be just some the waste that goes down the toilet. It can be whatever is causing the demand for oxygen in the wastewater. So here I've got a microbe who's eating a hamburger, but unfortunately the bugs aren't getting something as delicious as a hamburger in the aeration basin. They're just getting whatever is there. It's any sort of energy source that they can subside on. So let's talk about the reaction. We've talked about kinetics. Remember, there's zero-order kinetics, first-order kinetics, second-order kinetics. We've actually tackled that a couple of different classes, both using Excel and just taking a look at what the data looks like when it's plotted. So here is our reactor, and there's air being added to the reactor, and some reaction is happening in there, the reaction of the bugs eating food. And sometimes what we do is we assign the variable J to whatever constituent we're keeping track of as the reaction. So there's some J that's coming in and some J that's going out. For our purposes, the J that we're interested in is the concentration of oxygen demand. And so whatever it is in there that is going to cause the bugs to eat the food and simultaneously demand oxygen, then that's what we'll be keeping track of. And the effluent concentration is going to be lower than the inflow concentration. That's the whole point of this reaction, is that the bugs are eating the food, and the food is this pollutant that we don't want to get into the river. So here is the expanded version of the mass balance equation. Remember, just a moment ago, we were only considering the flow in minus the flow out. And we said that is accumulation. But we can expand that to say, let's consider the reaction inside the tank of something being produced or being consumed. And those two things can happen simultaneously in the same reactor, although for our purposes what's happening is the constituent J, the BOD, is being consumed. So the BOD isn't being produced inside of the aeration basin, so we can cancel out this production term. What we're left with is this expression that says the changing mass versus time. So over time, what's the rate of accumulation inside of that tank? It's the flow rate in minus the flow rate out, and we're talking about the flow rate of whatever this component J is, not just the hydraulic flow rate, it's the rate of the mass that we're tracking, constituent J. Plus or minus R, where R is the reaction rate, times the volume of the reactor. So it would be plus if it's a production reaction, and it would be minus if it's a consumption reaction. So this is nice and simple. This may be the simplest equation we look at tonight. We get into some pretty bizarre equations this evening just because once you have recycling solids like we've got in an aeration, in an activated sludge aeration basin, things get a little complicated. So let's take a look at this diagram that's presented in your book. It's just a diagram of suspended growth reactor. And by suspended growth, what we mean is that the microorganisms that are growing, they're floating inside of the tank. They're not living on a surface. Like they say there's always germs on handles of doors. You know, like if we zoomed in with the microscope on this door handle, we'd probably see germs, right? That's attached growth. This is suspended growth, where the bugs are floating around inside of the aeration basin. What we have is a flow rate of the wastewater coming in, Q, and you'll notice that the flow rate coming out of this system inside of the control surface is the flow rate Q minus the sludge flow rate, because we actually have two streams coming out. We have the clean water is the effluent. That's clean after it's been treated. And then down here is the sludge that we're sucking from the bottom of the clarifier. You'll notice that there's the stream branches. Some of the sludge is returned to be recirculated into the aeration basin, and some of the sludge is wasted. If we didn't waste the sludge, then solids would accumulate inside of this loop, and both of the tanks would fill up with solids. And so we have to have some wasting of solids, and that's why there's this underflow that's going to a separate treatment system. Who can remind me why we return the activated sludge to the aeration basin? Doesn't that just make the water dirty? When you think about it, the clarifier, all of the solids are going to the bottom of the clarifier. And so you're taking solids and you're injecting it to the aeration basin. But I thought the whole objective is we want clear water coming out of the clarifier. If we want this water to be clean, why are we injecting solids into the aeration basin? Go ahead. Very good. Exactly right. Yeah, the solids that settle to the bottom of the clarifier, that's rich in cells, and when they've been in the clarifier and down at the bottom, they're not getting any new food because the food concentration is high from the influent. I mean, a typical influent concentration of oxygen demand, it'll maybe be 200, 300 milligrams per liter. So there's a lot of oxygen demand coming into the aeration tank. But when they're sitting down here in the clarifier, not only are they not getting food, but they're not getting oxygen either. There's no aeration in the clarifier. If we aerated the clarifier, then the solids wouldn't be able to settle. So you notice there's no mixing that happens in the aeration tank. So by the time they finally get over to re-injected into the aeration tank, they're activated. The sludge is activated. And what that means is the sludge is ready to start eating. So that's the purpose of the recycle. And you're going to have to be able to explain that process in our exam. You know, there's a lot of calculations and problem solving in this course, but also a conceptual understanding of how and why return activated sludge works is important to be able to describe. Okay, so let's just take one last look at these variables before we move on. So Q is the flow rate. That's the liquid flow rate, the volumetric flow, and so it has units of cubic meters per day. X is the concentration of biomass inside of the aeration basin. Now biomass, that means there's a lot of different components to the biomass. Biomass includes the bugs that are alive and hungry. The biomass includes the bugs that are dead, because some of the bugs inside of that are being recirculated, they're no longer living. And so it includes both of those components. And it also, the biomass also includes non-biodegradable constituents. Okay, S is the substrate, so it's the concentration of food that's soluble. There may be some oxygen demand that's in particles that are floating around inside of the water, but the particulate BOD can't be consumed by our microorganisms. The microorganisms are only able to consume the oxygen demand that's dissolved in the water. So S includes only the soluble. Soluble means that it's mixed into the water. Some of the BOD may still be particulate, and the bugs won't eat that. V is the volume of the tank, and then there are these subscripts here. 0 means the flow coming in. R is talking about what is recycled. W is waste. How come you see the R here for XR and XR? How come they didn't say XW? Because this is the waste stream. Why do you suppose that they're putting XR there instead of XW? Exactly. Yeah, they're the same. I mean, they could have, but then we just say XR equals XW because it's split. It's the same stream that we've just split different directions, and so it has the same concentration of solids, but the flow rates are different. So that's why QR and QW are different. It's because the flow rate is not the same. Okay. And then S, look at all the places where S is the same. S is the same in the aeration tank. S is the same in the clarifier. S is the same in the effluent, in the sludge, in the activated sludge. Everywhere, because we assume complete mix, the substrate concentration is the same except for what's coming in. You'll notice here is the inflow concentration of substrate. So any questions about this diagram? Okay. So now we're going to start our long march through equations. And there's just no way around this. The design equations for activated sludge are very complicated. I would encourage you, if you're not already doing this, I would encourage you to read through section 7.6 of your book. You know, we only meet for 2.5 hours each week. And in a graduate course, you're not going to learn what you need to learn just from the words that come out of my mouth and the slides that I put up on the screen. In graduate level coursework, you have to think about it outside of class and read the textbook. And section 7.6, which was what we're going over tonight, it's sort of the heart of the whole course. Like all of the theory for how things work is distilled into this one section. So I'd encourage you as a supplement to tonight's lecture, really spend some time reading through section 7.6. The equations I'm showing you tonight are about 1/5 of the equations that are in that section of the book. I've basically shown you the punchline, you know, the conclusion of all the derivations they do. And you don't have to like memorize or put onto an equation sheet all the derivations, but it is useful to understand the relationship of these equations by looking how they've been generated. So with that said, solids retention time, which we're going to abbreviate with SRT, in some other texts or sometimes when you're talking to engineers, they'll call that mean cell residence time. And that just means it's the average amount of time that a cell spends inside of the looping system before it is ejected. Remember that water is flowing through here, but the amount of time water spends in the system is different from how much time a cell spends in the system, because the cell might be recirculated several times before finally it exits as sludge, or some of the cells also exit in the effluent. So the solids residence time, SRT, is different from the hydraulic retention time, which we assign the variable tau. Now the hydraulic retention time is easy to calculate. It's just a matter of the volume of the aeration basin divided by the volumetric flow rate Q. But if we look up at the solids retention time, how long the solids spend inside of the system depends on the concentration of solids in the mixed liquor, X, the volume of the tank, and then the ratio, the relative ratio of the waste flow rate and the recycle flow rate. So you have to think about it in terms of probability. If you're going in a loop, how many times you're going to go through the loop depends on the ratio of the flow rate to return versus the ratio of the flow rate to exit. If there is 1 unit of return for 1 unit of waste, then you'll make 1 extra round trip on average before there's an exit. But usually the return flow rate, QR, is much, much larger than QW. And so a cell will, a typical solids retention time might be on the order of 5 days, whereas a typical hydraulic retention time would maybe be less than 1 day. So a cell is going to make many circuits through the clarifier and into the aeration basin before it's finally ejected. Any questions so far? So if the system is in steady state, and you can achieve steady state in the secondary treatment if you have a flow equalization basin upstream. So steady state means that the flow rate is constant, the inflow concentration of BOD is constant, basically nothing is changing with respect to time. Then there is a growth rate, the net specific biomass growth rate is the inverse of the solids retention time. And this idea is one of those things that the book goes into a little bit of detail explaining, that you can actually control how quickly the microorganisms are growing by controlling the valve that sends some of the flow to return activated sludge and some of it to waste. That actually, the person who's in charge of this treatment plant, the operator who's at the control switch and is making adjustments to the flow rates, that operator controls the growth rate of the cells by the decision of how much of the sludge is returned versus how much of it is wasted. Because basically, the longer the cells spend inside of the recycle, more of them, a greater fraction of them die, and their growth rate decreases the longer they're in there. And we've got a graph that illustrates that effect in a little bit. All right, so now we're going to have a couple of different mass balances. Remember, mass balance is the difference between in minus out is accumulation. This equation that we have here takes the idea of mass balance to say, if we have a reaction happening inside of the aeration basin, what is the concentration of the biomass? There's going to be several different x's tonight, even more than here you can see there's x, xr, and xe. There's going to be different components of the biomass that we'll calculate. Sometimes we want to know how much of the biomass is living, active cells versus how much of the biomass is decaying or dead cells. But this concentration X is all of the biomass together. And so what it depends on is the ratio of the hydraulic residence time and the solids residence time. You can see there. And then there's this term, synthesis yield coefficient. And by the way, if you go through the book, you can eventually find these definitions and the units, but they don't provide the definitions and the units often enough, in my opinion. Like, I had to really hunt way earlier in Chapter 7 to find the precise language, because from edition to edition they've changed the wording of some of these variables, and I wanted to make sure that the notes reflected the updated edition of the text. But I've done that legwork for you, so keep these notes handy as you go through and read section 7.6, because you'll inevitably be going through some of the equations and you won't be able to find the definition of what some of the terms mean.
Grant of biomass the same as grant of DSO?
Well, what we're going to be measuring the biomass is the volatile suspended solids. Now, there's total suspended solids and volatile suspended solids, and what we're assuming at this point is that anything that's volatile inside of the aeration basin is biomass, whether it's living or dead. So you were wondering about the units, right? Mm-hmm. Anything that's volatile, and remember that's if we put it into a furnace and it cooks off at 550 degrees Celsius, we assume that it's either a living or a dead cell. Okay, there's another term here, B. the specific endogenous decay rate coefficient. Now, that's a really long phrase. What it means, B, you can put this in the side of your notes, how quickly the bugs are dying. And so it's important not only how quickly are they growing, but how quickly are the microorganisms dying. Endogenous decay. That basically means that one kind of microorganism will die and another kind of microorganism will consume it. And so we have to keep track of those microorganisms whose life cycle ends inside of the loop. Yield, we talked about last time, and yield is how much biomass grows from a gram of substrate that's used. Can y be greater than 1? Is it possible for y to be greater than 1? That's right. Why not? Why couldn't you have a y value greater than 1? Right. If I eat 1 pound of hamburger, while I'll weigh myself on a scale, I step off, and I eat 1 pound of hamburger and step back onto the scale, it can't increase by 2 pounds, right? So you can only increase by maximum of the substrate that's used. But the reality is that a typical yield is around 0.4, which means that after the microorganisms there are losses to heat and losses due to motility, that they're putting on approximately 0.4 grams of additional weight for every gram of substrate that is consumed. Okay, so those are the things that I wanted to point out for this mass balance equation. And when we're using this, the kind of a tricky thing is that you're not always solving for the variable that's isolated in the equation. What I mean is, when you use this in tonight's in-class exercise, you use this equation to find the solids retention time. You don't use this equation to find the biomass concentration. Actually, the biomass concentration is given. And that's how it works in design, is the designer says, well, I'm going to go for a biomass concentration of 2,000. And then they make that happen by how much sludge they're recirculating. So it's sort of like when you're driving a car, you can press on the accelerator and you choose what speed you want to drive at. The person who's driving the wastewater treatment plant, they choose what concentration of biomass they want to have by how much sludge they're returning into the aeration basin. And so X is something they select, and then the solids retention time that arises out of that decision depends on the hydraulic retention time and the kinetics. So that's one important thing to remember, is it's not always this variable that you're solving for, and that won't be the case tonight. Let's look at this graph. This is a really interesting graph. It shows how the microorganisms are behaving depending on how much food we give them. Now, this is just for one specific wastewater. This is an example. This graph isn't always true for every wastewater. This is specific just to a sample that was taken at one treatment plant. And if we took a different sample at a different treatment plant, maybe the curve would look different depending on the characteristics of the wastewater. But what this is showing is, here on the x-axis, substrate concentration. That is, how much food is inside the aeration basin. So what is the S value in the aeration basin? And then on the vertical axis is how quickly the microorganisms are consuming the food. So let's look for the trend. The trend is, if you have lots of food, the microorganisms are consuming it quickly. Here it shows us they are consuming 600 milligrams per day if you have 50 milligrams per liter in the aeration basin. By the way, if the concentration is only 50, how can they eat 600? the concentration is 50 milligrams per liter. So how is it that these bugs are able to consume 600 milligrams per liter per day? Yeah, there's always more food coming in. That's the answer. It's the units are different. Here is milligrams per liter, and then that is milligram. What it really is it's milligrams per day per liter. And so there's always more food coming in for the bugs to eat. So it may, at first glance, be a little bit tricky because we're seeing that the concentration of food is 50. Here is the rate. They're eating 600 per day because there's always more coming in. So if we decrease how much food is available, how does the bug's performance change? They're eating less because there's less food available. And that's first order kinetics, right? First order kinetics that we studied last week and the week before. First order kinetics says that the rate of the reaction depends on the concentration of the reactant that's present. So if you're at a big feast and there's less food available, people slow down because nobody wants to be the last person to take like the last roll off the table, right? Well, the bugs aren't doing it for that reason, but as the concentration decreases, so does their utilization rate. So the maximum substrate utilization rate, we assign that to variable K. And you'll see that anytime you have a homework assignment or an in-class exercise, the kinetics for how the bugs behave is specified, and this chart shows how it's derived. What this is showing, the K value, is the ratio of the maximum rate, 600, divided by, in this case, the concentration X was 100, so 6.6 milligrams of BSCOD per milligram of VSS. Oh yeah, all right, because there's also the ratio of the TSS to VSS. So X, remember, is the concentration of the microorganisms inside of the aeration basin. The half velocity constant, though, is when you get down to half of the maximum. So if the maximum is 600, then half of that rate, half of the maximum rate is 300. What is the concentration that corresponds to that? So these microorganisms, they are consuming food the fastest when we have 50 milligrams per liter. And the fastest that they can consume food is 600. Even if we had 60 or 70 or 80, that curve looks like it's mostly stabilized. It's not still increasing. So this has reached a maximum for all practical terms. So half the maximum is 300. Come down here from where 300 crosses the curve, and that is 5 milligrams per liter. So that's the nature of the half velocity constant. Okay, so now we have to do another mass balance. The first mass balance was to find X. Well, it was the relationship between X and the solid's retention time. And it's actually the solid's retention time that we're solving for once we have a selected X value. Now this tells you what is the concentration that comes out of the clarifier. Did you find it strange on the homework that as you were working through that, the inflow concentration didn't affect the performance? Like you had the BOD coming in and the BOD going out. And I told you one of the values I gave you is the inflow BSCOD. But in all your calculations, you never used that. And that seems very strange that the concentration of BOD that comes in doesn't actually affect the concentration that's coming out. Not directly anyway. It does indirectly. But the outflow concentration, S, what it depends on is the solid's retention time, that half velocity constant, so that's a kinetic value that we were just talking about. B, remember that's endogenous decay, that's how quickly the microorganisms are dying. And then the ratio between the yield and the maximum utilization rate of food. So all of these parameters, nowhere is it taking into account directly the inflow substrate concentration. Now the reality is that solids retention time is going to be affected by the inflow substrate utilization. You'll see the indirect effect of the S value, but it's not direct. So we'll use this tonight to calculate the effluent concentration from a reactor that I'm asking you to analyze. You can find out the effluent concentration, and as I mentioned, the process performance. And by process performance, I mean how well is this reactor removing the pollutant that we have to have extracted from the system before this wastewater is discharged. Its performance is only a function of theta sub c. I should change that to say SRT, solids retention time. Theta sub c is the mean cell residence time. It's just a different name for the same thing. Solids retention time and kinetics. Solids retention time. Yeah, I forgot to update that. They changed the variables from the recent update. All right, so that's the mass balance on the substrate. Solids are being produced, and we like that because we can settle solids. We can't settle something that's dissolved. If you pour salt into water and you mix it up and the salt dissolves, it doesn't matter how long you let the water sit in the glass, the salts aren't going to come out of solution and settle at the bottom of the glass. They're dissolved. And the same thing is true of BOD. If it's dissolved, no amount of settling is going to take a dissolved constituent and take it to the bottom of the clarifier. So what we do instead is we turn that dissolved mass into a settleable mass, into new cells. And this is the most basic way for us to estimate the rate that solids are being produced inside of the aerating, inside of the secondary treatment. It includes the total concentration of volatile suspended solids in the mixed liquor. We multiply that by the volume of the aeration basin and divide it by the solids retention time. Now, it's a little bit confusing because in a couple of slides we're going to see a different formula for P sub x of just the volatile suspended solids. But what this includes is both the volatile suspended solids and the other suspended solids that go into total suspended solids. So this is just based on the solids retention time. Mixed liquor suspended solids concentration includes the constituents that are biodegradable, the biomass, meaning the active cells and the dead cells. So X is the biomass, both components of it. And then X sub I is the non-biodegradable volatile suspended solids. There are some components that may be volatile, like let's say gunpowder. If you mix gunpowder into wastewater, even if it dissolves, microorganisms can't necessarily break down gunpowder. There may not be a microorganism that can fix that in the same way that microorganisms can break down other dissolved volatile suspended solids. And so it's a small fraction of most wastewaters, this non-biodegradable component. But here's the formula that allows us to calculate both. And you'll notice it has three pieces. The solids that are inside the aeration basin include, we call component A is like the active biomass, the heterotrophic biomass. So these are the microorganisms that are alive and active. And you'll notice that it's a function of the solids retention time, the hydraulic retention time, the yield coefficient, the difference between the inflow and the outflow concentration of the substrate, the endogenous decay, and again the solids retention time. Now cell debris, these are the dead cells that are floating around and they're not breaking down BOD, but they still account for a part of the biomass that's there. Cell debris is dead cells. They're not breaking down They're not active. And then finally, that component we were just talking about, the non-biodegradable VSS, we can calculate that. This variable x naught comma initial will be specified in problems as the non-biodegradable VSS that's coming into the reactor. So that might be, priority organic pollutants like chlorinated solvents or gunpowder or whatever it is that microorganisms aren't able to break down. Okay, so we're talking about solids production. We've already had one slide that was on solids production. Let's jump back and remind ourselves what that simple equation was saying. So here is solids production, the total solids. Here, this is the solids of just the volatile suspended components, and it's a little bit more extensive because it's including the effective cell debris and also the non-biodegradable VSS. The first way of calculating the solids production didn't really have the same level of detail as this does, because this is taking into account the rate that the cells are dying, the fraction of the cell debris relative to the active cells, and so you can get a little bit more accurate representation of how much mass is being generated when you use this approach. The text makes the point that usually about 85% of the total solids are volatile, and the other 15% are fixed solids. And you remember from your homework we did a problem where we were distinguishing between fixed solids and volatile solids, and I gave you the example that if we had a dish and the dish included a little bit of coal and then it also had some sand, both of those are solids. But if we put it into an oven, the coal will catch on fire and it will volatilize, and all that's left is the sand. The same thing is true in wastewater. Even though we're going to do grit removal, and even though we have a primary clarifier, there's still going to be some solids that aren't volatile. Most of the solids, once we get to secondary treatment, are organic or volatile solids, but the book says about 85% is volatile and 15% is fixed, and so this allows you to calculate the total just by dividing what you calculated in the previous step by 0.85. So it scales it up. There's one more term, though, is it's keeping into account the difference between the volatile and total solids in the inflow, because it's not just the reaction that's taking into account, but also the in minus the out of the influent and the effluent. All right. This figure shows sludge age simultaneously with showing the relationship between mixed liquor volatile suspended solids and the overall biomass. Okay, so it's a little bit difficult to read because, as you'll notice, there's two different vertical scales. This curve, the arrow to the right, that means you read the units, the vertical units, off of this graph. So biodegradable, soluble, COD or BSCOD, basically this means effluent concentration. And so the longer the solid's retention time, the lower the effluent concentration. If we have the solids in the aeration basin for a long time, treatment is more complete. So if we have a low solids retention time, down here 1 day, 2 days, our performance isn't as good. There's still 12 milligrams per liter of BOD in the effluent. But if you want to have a really good low concentration of BOD in the effluent, you have to have a high solids retention time. Well, to have a high solids retention time, that means that you have to have bigger components. You have to have a bigger volume for sludge storage in the clarifier. You have to have a bigger aeration basin so that your mixed liquor volatile suspended solids concentration isn't too high. Now on the secondary vertical axis, this is where we're looking at the difference between mixed liquor volatile suspended solids and the biomass. Okay, so MLVSS, that includes the living cells and the dead cells. And you'll notice that it diverges. The longer the solids retention time is, these two lines are getting further apart. And the reason why they're getting further apart is because there's more cell debris. You have a greater fraction of the biomass is non-living cells. The longer you're recycling it over and over and over again, there's going to be a lot of dead cells in there. And so, you know, it's sort of, the dead cells aren't removing substrate, but still they're requiring you to pump them, and it's increasing the volume of sludge in the system. So there's a balance to be had. You don't want the system to be too big because it's costly, but having a big system enables you to have really good performance. And so what we're trying to do is, somewhere on this line, it's diminishing returns. You know, like 5 days of solids retention time, most of the performance has been achieved. If you double it, it's only a small improvement in performance. It goes from, if you go from 5 to 10, it looks like you're going from about 2.2 milligrams per liter down to maybe 1.2 milligrams per liter. Doubling the solids retention time only has a small improvement in the effluent concentration. So it's pretty rare for a system to have a really long extended solids retention time unless we're trying to do other things like denitrification or remove phosphorus, because there are sometimes good reasons to have a really long solids retention time if you're going for nutrient removal. We get into that in chapter 8. Any questions about this figure before we move on? No. All right, we'll take a break in about 5 minutes.
I guess maybe that last statement, the SCOD concentration is very low after SRT 2 days.
Mm-hmm.
Is that, again, just for this particular wastewater, or is that the general rule?
Good point. I should have pointed that out. This is just one particular water. You know, every water is going to be different, and so depending on where the waste is coming from, you know, it could be food processing waste that's really high in simple starches, and they're broken down super quickly. And so in that case, maybe the curve would be even shifted to the left if it was simple sugars. But if you're getting waste from a, I don't know, like just a regular municipal waste that isn't quite as many simple sugars, then the curve may be pushed to the right. So it's just in this particular instance that it looks like most of the removal has happened after, I don't know, maybe 2 days isn't right. Maybe I should change that to say 4, you know, because this starts flattening out, you know, diminishing returns, I'd say, is about here. So I'm going to change that just to say 4 days. But the main point is just most of the gains are early on. But I'm glad you asked your question, because I meant to emphasize that, like some of the other graphs we've seen tonight, this is just an illustration using one sample water. You know, the same trends are observed in other places, but the curves will look a little bit different. Okay. So as you read through section 7.6, read through the text that describes this figure, because this is one of the figures that, you know, I may ask you to, I may give you a test question that says, what's happening here? Just tell me the story of this picture. And, you know, it would only take maybe 2 or 3 sentences to tell the story of this picture, that this picture is showing the relationship between solids retention time and effluent concentration, and then the reason for that diverging gap between the mixed liquor volatile suspended solids, which includes everything, and then the active biomass, which is below it. Okay. There's a difference between the theoretical yield and the yield that's actually observed in real life. And when we were talking for the first time about theoretical yield, we assigned it the variable y, and what we said is, very simply, yield is just the relationship between how much biomass is produced versus the mass of substrate that's utilized. And we said, you know, it can never go above 1, and usually it's maybe even below 0.5 or in the range of 0.4. Well, observed yield, what we actually get in the field, is different from this lab value of theoretical yield. You know, y is maybe something that we would derive in the lab in a batch process over the short term. But over the long term, in an actual wastewater treatment plant, we're going to have B, endogenous decay. This theoretical yield doesn't take into account endogenous decay. So it does not take into account the accumulation of cell debris, and it also doesn't take into account that sometimes a part of your wastewater's VSS can't be biodegraded. And so this observed yield takes both of those things into account, in addition to the relationship between the heterotrophic bacteria and how much food they eat and how much weight they gain. So you'll notice, you know, Y, this lab yield, the ideal theoretical value, is a component of the observed yield, but what happens in the field is more complicated than that. All right. I think this is the last slide before we skip to the in-class exercise. Yeah, okay. So we'll talk about this one, and then we'll take a break and get ourselves psyched up for this much maligned in-class exercise. In the homework, you had a problem like this, and we did, was it an in-class exercise or the example, where we also had the demand in minus the demand out, was the difference between the two is oxygen demand. Well, that's the same thing here. The amount of oxygen demand inside the aeration basin is going to be the removed amount of BCOD. So removed is the difference between in and out. But then there's also the COD of the waste sludge that we have to account for. If we go back to this, there is going to be some discharge of oxygen demand in the underflow sludge. And so that's another term that we subtract. So BCOD removed, that already has BCOD removed is the oxygen demand in minus the oxygen demand out. So what we're saying is that the overall oxygen used is how much oxygen demand went in minus the oxygen demand out minus the oxygen demand that's in the underflow sludge that's being wasted. Okay, so that's the simple idea of it. But what we have to keep in mind is that if we try and in the lab oxidize all of the BOD with a chemical reaction, there's going to be some of the BOD that the microorganisms can't break down. You know, maybe we could break it down chemically, but the bacteria aren't going to be able to consume all of the, there's the non-biodegradable VSS that we have to take into account. The other thing is that the bacteria are using some of the BOD for their cellular respiration. And so they're generating heat, not a lot of heat because they're very small. But you know, when you eat a hamburger, some of that food that you eat is expelled to energy. You know, like you're heating, if you go in a small room, you heat up that room with your body heat. So the idea is some of the energy is being lost to heat, and so there is a difference between the biological demand for oxygen and the chemical demand for oxygen. What we're going to experience in the field, in a real wastewater treatment plant, is the biological demand for oxygen, which has to account for energy uses, cell growth, endogenous decay, and the fact that solids retention time affects the solids production. And so here's the equation that we'll use in the in-class exercise to find out the mass per day. The units for R, if you divide this whole thing by 1,000 grams per kilogram, because S naught we put in terms of grams per cubic meter. So usually the oxygen demand is expressed in kilograms per day, but flow rate is cubic meters per day. S naught would be grams per cubic meter, so we have to divide this term by 1,000 to get the kilograms per day that we want. Anybody remember what is 1.42? What's the origin of that strange coefficient? Okay, it is very good. It's the grams of oxygen required per gram of cell tissue. So if we have 1 gram of cell tissue, then it would require 1.42 grams of oxygen to break down that tissue. So when we are generating cells, that reduces the oxygen demand because those cells are going to exit the system. All right, so let's take a break. We've got 5 minutes. We'll get back together, and I'll ask you to get into groups, and we'll start working through this in-class exercise. Okay, so we're going to do in-class exercise 5 now, and what we have in this in-class exercise is, let me hand it out, and I'll bring it up on the screen. Go. Here's the in-class exercise, which I will email out. All right, well, let's go through a couple of things about what you can actually design. When you have a situation like a wastewater treatment plant, there are certain parameters that you're in control of and certain things that you don't control. For example, you, the designer, do not control the flow rate. You know, unless you decide to split the stream into multiple parallel tracks, just the flow rate is going to be whatever the flow rate is because of people's use of water and how much they're adding to the storm sewer, or how much they're adding to the sanitary sewer. But we can adjust what we use as the volume of the aeration basin. And of course, the objective of all of this is just to reduce the amount of substrate in the effluent. So we can adjust the reactor, and when we do that, it has an impact on the solids retention time. We can control, well, we can design in advance, and actually some of these things can be changed on the fly by the operator, and certain things can't. You know, the operator can't adjust the reactor volume. You know, the tank size is fixed when the plant is constructed. When you're doing your design, you select a sludge recirculation rate, but that is that's something that can be changed on the fly, you know, as conditions require. You know, a ballpark figure is that typically 20 to 30% of the wastewater flow would be a typical sludge recirculation rate. And when you change that around, what you're affecting is the food to microorganisms ratio. And we'll go into more detail about what this ratio is and what it means. You have to decide how much air is going to be provided to the system, and usually it's wise to supply an excess of oxygen, more than you think is going to be required, because if the temperatures get really high during the summer, then that can decrease the efficiency of oxygen transfer, and so you always want to be on the safe side in supplying plenty of oxygen. That shouldn't be a limiting factor in the aeration basin. Another thing we have to take into account is downstream of the aerator, how good will the clarifier be at settling the solids and making sure that you can return sludge into the aerator and that you're not losing too much X through the effluent. Remember, X is the concentration of biomass, and we only want the biomass in two places. We either want it in the sludge that's being wasted, or we want it in the recirculated sludge so that it can get back into the aerator. Inevitably, some of it will get into the overflow of the clarifier, and so some of it will be in the effluent, but we don't want it there. Now, during operation, we can adjust the solids retention time by affecting the sludge recirculation rate. And what that does effectively is change the ratio of food to microorganisms. So let's talk about this thing of food to microorganisms. What it means in broad sense is it's the ratio of how much substrate is utilized, and you'll notice that has units of grams of biologically soluble carbonaceous oxygen demand per day. So that's the food that gets consumed per day. It's a rate. And then the mass of microbes. And the mass we're talking about is the mass inside the aeration basin. And so it's calculated as the volume of the aeration basin times the concentration. And the typical concentration will be in the range of 2,000 to 4,000 grams per cubic meter. If we want to change the performance, we can control the food to microorganisms ratio. And there are some very specific consequences to how much food we give to microorganisms. If we give them a lot of food, so let's say we have a high F to M ratio. High F to M ratio means we have a very high concentration of substrate relative to the concentration of microorganisms that are in the aeration basin. So there's not very much X, but there's a lot of S in the case of a high F to M ratio. What that'll mean is that you have a lot of sludge that's being wasted. And that can be expensive because when we waste sludge, it doesn't just instantly go to outer space. You know, this sludge here is going to be very costly to handle. We generally will digest it anaerobically, and that's an extremely slow process. You know, however much sludge we're wasting, it has to be contained for between 30 to 60 days, might be a ballpark digestion time for sludge, for anaerobic sludge treatment. And so that's going to be a very, very large containment vessel to store that much sludge. And then the other thing that's very expensive about this wasted sludge is we have to dry it out. You can't take sludge directly to the landfill. The sludge that goes to the landfill is, I think it was maybe Lee was talking, was it Lee that was talking about, I don't remember who it was. It was talking about the sludge can't drip. Who was saying that? You know, before you landfill sludge? Maybe it was Lee, since he's not. All right. So the idea is that before you take it to the landfill, the sludge has to have the moisture removed from it. And so you're either drying it out or pressing it together. In some places they'll lay it out on a bed outdoors and allow it to dry, and then they'll scoop it up with front-end loaders. But it's very costly, this waste sludge. And so if we talk about a high sludge waste rate, that's going to be costly, but we have a short sludge retention time. So you're either going to have a small aeration basin and a high sludge waste rate, or you're going to have a big aeration basin, and you can have the F to M ratio much lower, and if you have a low F to M ratio, meaning a long solids retention time, then it's more efficient because the microorganisms are breaking down other microorganisms. Instead of only breaking down the substrate, instead of only breaking down the soluble BOD, the microorganisms are sort of cannibalizing one another. And so if you have a long solids retention time, you have a much more diverse population of microorganisms, and that degrades the waste more completely. And so the typical range of food to microorganisms would be in the range of 0.1 grams of food per day for each gram of microorganisms, all the way up to 1 gram per gram. And you'll remember that the yield is on the order of maybe around 0.4. And so if you're getting 0.4 grams of microbial growth for every gram of food supply, then that means that in this range of food to microorganisms ratio, you could have the bacteria doubling in number every 2 days, potentially, and just for the ballpark range of the population that's there. The effects of the F to M ratio are classified in terms of overall process removal efficiency. This is one of the final things that was in section 7.6, is looking at the difference between the inflow substrate concentration and the effluent substrate concentration. And then another just a parameter that's used to describe how the system is being loaded is the volumetric loading rate of organics. And so the volumetric loading rate for organics, this is the inflow substrate concentration, the volumetric flow rate, the volume of the aerator, and then since all of these units would already be in terms of grams per day, then it puts in the conversion for grams to kilograms, so that the organic volumetric flow rate, loading rate, is kilograms per day when you make that conversion. All right, well, we're going to leave it here for tonight. When we get together next Wednesday, I'll give you a copy of Homework 3, and we'll continue talking about modeling of complete mix, and we'll actually get into suspended growth. I'm sorry, fixed growth as well, attached growth. So have a great week, and I will see you next Wednesday.